Okay, we're back again. Same evening. Sorry, same wee hours of the morning. So I had a comment about Blink not working and stuff like this. So I tend to, when I get a controller, one of the first things most people do, I guess, maybe not, is run the Blink program. But depending on the microcontroller, Blink is done differently. Like, so some controllers have just an LED on them now. Some controllers have a Neopixel, Adafruit's term for the multi-LED little box type of LED. And some you can't even choose which pin it's even on because they decide which one they're going to use. They might dedicate a pin to it. Others will share a pin. So what we're going to do is we're going to go through a bunch and show them off and how they're done. So we have a row of them here. So our first one here is our classical Nano, Arduino Nano. Okay, so this is actually kind of a new version of it. It's still the basic Nano, but it is the one with the newer bootloader in it. It is also the one with USB-C. So I kind of like this. I wish that some of the other guys here would have just turned these into USB-Cs. Like the Pico could have been done, because the connector's not that much bigger than these guys. You can see that. So this is the Nano. We're going to do this. This is Arduino code, so it doesn't do CircuitPython or anything. Then we have the Pico here, and I happen to have it in Arduino mode, but I could have done CircuitPython mode, or I could have done MicroPython mode, or I could have done actual Arduino, Raspberry Pi SDK, but I'm not built. I don't have a built-up system to actually do their SDK. Then we have what they call a SAMD21 Mini. This is a knockoff thing, right, from China. This has got some interesting quirks, and we'll get to it when we actually do it. Put it in here. This is an actual Arduino Nano Connect. This is the new one they came out with last year. I just happen to have it in a breadboard. It doesn't have to be in it, but see, like so. So it's the actual one from them. In fact, I'll just leave it out of the breadboard for the moment. Then we have a ESP32, not an S1, S2, S3, C3, whatever, just an ESP32. Okay. Then we have 8266 ESP. So this is technically even older than that one is. Okay. And this one happens to be from Lowland. They call it a Node MCU. And sometimes when you're searching for stuff in Platform.io, knowing this will help you find the actual board. But you can get away with the ESP dev kit basically for these things. This little guy here is an Adafruit Itsy Bitsy RP2040. So the same chip as the Pico, but they do their lighting a bit differently. So we're going to look at that. And then the granddaddy of them with some really weird coding is this guy here, which is an ESP32S3. And we're not too worried about memory sizes or anything like this. We're just doing Blink. So this has its own stuff. So we're going to be doing ESPIDF on this. I believe this is CircuitPython. This is Arduino. This is possibly in CircuitPython. I have to look. This is CircuitPython. This is Arduino. This is Arduino. Okay. So let us begin with our first candidate here. And I'm going to just flip to the code window. And we're going to plug this in. Since it's USB-C, I need a USB-C cable. Just like so. You can see it in the little window. Now, of course, actually, let's go over here to the desktop so that we can go to the console for a sec. And we'll just do a D message here. So we want to know about this part here, of course, right? This is our device. You're not going to get much of a name out of it, right? So you can see, like, for example, when I plug the macro pad in, it says blah 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 macro pad. When I plug this one in, it's like unknown whatever, right? That's what happens with a lot of the Chinese. It's not fully fleshed out for their USB ID. So, but what we only care about is USB 0. So we can go back to here and we say open folder. I think I might have made a workspace out of it, but we'll find out in a sec here. I go to projects, and I believe I put it in my Blinkit, and yes, there's a workspace for it. So let us go instead open workspace. No, work projects. There we go. Blinkit, number 1. We open this workspace. Okay. So I could have done this in the Arduino IDE, but since I have my platform I/O rigged in my Visual Studio Code, I do everything from there. Let me just move this back so I don't hit it with the cable. Okay, so this is your standard Blink program. Okay. Now, one of the things that will catch you sometimes on the standard one is this right here. So that LED underscore built-in is in the libraries. Now, the other thing, of course, in Platform I/O, when you're dealing with Arduino, and they fixed this bit apparently, so you don't have to actually do what I have done anymore. I generally convert my program here into CPP files, C++ files, right? If you do that, you have to add this header in. If you leave it as INO file, then you don't have to do this, because Platform I/O now picks up correctly that an INO file is an Arduino development file, and it should include this automatically. But this guy here is a built-in function. It's in here somewhere probably, and it just simply tells that pin 13 on these guys is tied to the LED. And you can actually, it's kind of hard to see on that. It is blinking at the moment. Now we know it's blinking. We can change the blink rate. So let's shorten this and let's lengthen this. And we will push a new copy to here. So if you get this sort of thing, that's because of this. It thinks it's on ACM 0. Sometimes this thing does not pick up. So I'm going to go open my platform NO here. And we will find Mr. Nano new here. And I'll just say upload underscore port, right, equal dev tty USB 0. And I will make sure that we are using that one like so. And we'll try again. There you go. That knows. So I've changed the blink rate on this. It should be longer and a quicker blink. There you go. So now 2 seconds with 1/10 of a second gap. There you go. So this is your classic Arduino blink. Straightforward on these things, no issue. So let's get out of here. And let's go to Mr. Pico. Now this one uses a different connector. So I have to change cables here. When you're doing any of these guys, be very careful that you don't bend upward. You could lift the port off the board, and then you'll be without a board. You'll have to fix it if you can. Alright, so right now this one is blinking here. You can see that. Now let's open this. Let's see if I think I have a workspace for this one too. So open workspace from file, projects, blink it, and RP Pico. Yeah, I do have one open. Now for the most part this one works exactly the same, but you can see that this one doesn't have that in there. LED built in is actually not even on a number. It literally is a pin. Okay, to them anyway. So let us just see if we can push to it, make sure we can do it. There we go. You can see here, compile, completely different tool. We push the code, and it thinks it's on ACM1. Now we should check, make sure that that's what actually happens. So demessage, and it is ACM1. So in this case, it did correctly find the correct port. Then it flashed it, and okay. Now we know it's going to work because we can just change this. We'll change this to 2, 1, and we'll make this blink a little differently. So right now it was blinking 1 second with a 0.2 of a second wait. By the way, yes, 1000 here is 1 second. So I'll write a new one now. And you can see now that this thing is very short, long blink. Very short, long blink. Okay, so it is working. But you can tell in this one, the pin in here is literally called LED built in. Whereas in the Nano, technically it's pin 13. So if you were to substitute 13 into these functions in the Nano, it would still work properly. Now that is important to note because on other controllers they are on different pins, and this doesn't exist. And then that makes it like the blink program not work. So let's close this one off and we'll go to our next one. Our next one will throw us a monkey wrench. Okay. So here we have the SAMD one. Okay. And you can see I have a CircuitPy drive on here. Oops. I need to mount the second CircuitPy drive. Yes. Now to this, it's known as Arduino Zero. If you're looking for the CircuitPython and whatever. Now, technically this might be wrong firmware for this, even though it works, because the pins might not be correct for this. I did have a look at the pin mappings to see, and all the pins are covered. Right? Now, Adafruit has an Uno looking board that's an Arduino Zero. Right? And this is more of a small, tinier version of the board. But the pins seem to match. So let us open it up. File, open workspace again. I think I have a workspace for this one too. So, San generic. Oops, we don't, because this was CircuitPython. Oops, okay, no problem. We open the CircuitPython directory. Okay, now we really changed the way the Blink program works in here. So now we're in CircuitPython code. We load our required stuff, board, digital I/O, time, so we can have a timer. So what they're doing here is they're saying, well, we'll define LED, and it's on this thing, board LED. Okay. Now you're probably wondering, well, how do they know what it is? Well, if you connect to the serial port on this, ooh, that's not good. Yeah, okay. So we have an issue here. We are not finding our serial port. Let's go. Usually this is the case if can't find the board definition or whatever. So I'm just going to check here. Oh, we updated 2022-02-06. I'm going to go into here. It's currently 05. So I need to change that to 06. Control S. And it's probably also wrong in the workspace here. Is it 2005? Yeah, it is. I don't know what it is. This does some. Whoops. This sometimes doesn't update. Neither one does. This one usually does get updated, but sometimes it doesn't. So, goink, goink, goink. Okay, so we don't need that anymore. Let's try now again. No, we might have to reopen this up again. File, close workspace. File, open workspace again. Open. There we go. So Control C. There. So if you do this, import board, and then dir board, we have all the pins. Here, let me. There we go. So you can see that all the pins are in here, including one called LED. So they're just referencing, they're saying digital I/O, in, out, pin, LED, and then they're telling the direction output. So we're sending to this pin. Okay? Then they're saying if it's true, it's on, I think, and if false, it's off. It might be actually the other way around in some, where true is off and false is on. But we can change this, but you might notice that, yes, we have some LEDs on here, right? But there's no blink. Well, if you look carefully at this board, there is a fourth LED position in here called L, except it doesn't have the LED soldered on, and the circuitry around it is not there. So what I found out is in this dumb little board, for some strange reason, they didn't solder in the indicator LED. They soldered in the receive transmit LEDs, which are the blue ones in here. It's kind of hard to see because it's a little too bright. And then the green LED on here is I've got the board on, right? And you'll find also some controllers will use the on indicator LED to indicate blink at the same time. But sometimes they won't let you do both at the same time. If they're indicating that the board is on, they won't let you blink the LED. So it's really stupid. This particular one is the one with the monkey wrench. So it doesn't matter what I do up here. Technically, it's blinking the LED right now. Problem is, the LED isn't there. Now, I don't have one of those Adafruit Arduino Zeros. I don't have one here. So I cannot cross-check this board against its bigger brother, the one that looks like an Uno. So this is one that is a gotcha. So we'll close workspace on here. Pluck it out. And let us put in Mr. Actual Arduino. Ooh, I didn't dismount the drive on that one. That was a naughty. So, File, Open Workspace, Circuitpython. So we have basically the same code, but we'll have to fix JSONs because 06 here. So let us just check here. Did this one get an update? Yep, this one got fixed. See? Fixed. 06. So let's open up the other one, the settings JSON. And it's wrong. It's 05. So that's okay. Control S. And I'm just going to reload this workspace again. Close workspace. Open workspace. Now, if I click the magic little serial monitor, yeah, there it is, right? Okay. So we have exactly the same code. And on this one, down there, there's our blinking LED. So it's a separate LED on this one. Now, if we do our pin drop, let's do it. Let's look at our pins here on this one. So, see, this is printing the words out too. I might have actually added that to the code myself, just to see. So import board dir board. So we look at here, got a lot more pins, but there's Mr. LED right there. Now this is quite a packed board, as you can see. We've got I2Cs, we've got SPIs, we've got microphones, we've got I'm not sure what the ESP stuff is, but we have a whole bunch of stuff buried in this board. It's a really well packed board. It's kind of like Adafruit doing it. So, and we see the blink is working. So let's change the blink. We'll just start the code back up again. And we'll change the sleep rate to 2 seconds and the off rate to 0.5. Two seconds, half a second, 2 seconds. There you go. So we know blink is working. And I will just close this workspace. Now I'll be pretty nice and actually dismount the CircuitPython drive correctly. I didn't do it on the other one. So that is the stock one, and it's easy. Separate LED. Now we come into an interesting one, and that is the first of our ESP. So this is the ESP32 room. Well, they call it ESP room 32, but it I've seen it referenced differently sometimes. So we have a blinking LED. Now this one, we're using, I believe, the platform I/O stuff on this one, because I think we have this in Arduino mode. But I could actually program this, I think, with ESP-IDF at this also, the same thing. So let me just go, and I believe on this one I have just to open a folder. Projects, Blink, and we go from the room. There we go. Oh, I do have a workspace for it. That's okay. So let's go do that. Whoops. You know what I wish was in this tree? Open workspace. Wonder why it's never there. I always have to go to that tree. Room, workspace, open. So we don't need a plant, we don't need that. So I have done, in this guy, I upped the speed of the writing to the thing, right here, 921,600. Now this guy here is basically the same as the Arduino code, but I redid it. So if you put in that default LED pin one, it won't work because it doesn't know what this is. It doesn't actually have that in here. I'm just going to check VS Code because I have a feeling launch extensions just no, that might be okay. Yeah, okay. We don't have to worry about that in here. I was thinking of CircuitPython paths crap. So I define a definition, and I know this guy here is mapped to pin 1. Now the other cool thing of this, it's not a CircuitPython drive, so I can hit the reset and stuff like this and not affect what's going on in here, because this is local to the hard drive. This is not on a drive on here. So we can change this. So let's change this to 2 and 1/10 of a second. And let's push the code. Let's see if we can push. We're not pushing. Could be this right there. So just a sec. I have to verify the port here. Key message. We are on TTY USB 0, not ACM. So go here. Upload underscore port equals dev TTY USB 0. Let's try now. We rebuild it. There we go. Right. Now, I found that these particular ones from AliExpress, I rarely actually have to hit the reset key while telling it to start writing. Some of these ESP stuff, you actually, when that line starts here, this right there, the connecting line, you actually have to hit the reset and hold it and then let it go when it starts writing. This one is pretty good. It doesn't have to do that. Just be patient. It'll actually write. And if you speed up the writing speed, this will go dramatically faster than it is. It's quite capable of doing the max out of it. This is like 921,000 baud here, basically. Yes. It's just knowing the port that you're actually on. Okay? So, our Blink program is... This is the one where it's in reverse, by the way. Notice that high is actually off. Low is actually on. This is actually in reverse. Because you can tell on this thing because it blinks very short with a 2-second delay. If we were to change this here, we'll make this 1 and we'll make this 2000. And we'll push a new copy in. Now, see, 2 seconds on, little blink off. So this is one of the gotchas. This is where high is not on, high is off, and low is on. So we could turn this off, and this on. And this is really stupid. You'd think it'd be the other way around in this thing. No. Let's straighten our comments here. I always like nice formatted code. There we go. Okay. Now, nice thing about this, we can just pull the controller off. So we're going to close this workspace. Now remember, pin 1, right? Well, let's put this one online. And has a nice big fat blue one up in the corner there. Okay. Now let's go figure out what we logged on. TTY USB 0. Okay. So file, open workspace, projects, Blinky, and we're going to look at the 8266 ESP. Okay. Oops, I almost gave it away. What we're after in here, probably, it's going to try to do ACM. So we're going to do upload underscore port equals dev tty USB 0, control S, control L. Okay. When I first did this code, it's exactly the same as the other ESP. Okay. But this is actually pin 2, not pin 1. So if I put on pin 1, nothing happens on the board. This is pin 2. Now we can check here. So we have this on 1000. So let's make this 2000 and 100. So we're going to find out if high is really turning it on and low is turning it off on this one. it's in reverse in the other one. Let's find out if this one is. Again, I sped up the thing. So you can see on this one too, it's in reverse. Bringing it high is actually turning it off. Bringing it low is actually turning it on this. So this is incorrect. This is off. This is on. And we can see this, of course, by doing the reverse. 1, 2. So I've flipped it around. And we'll push a new copy. And now we can see 2 seconds and a quick blink. So that symptom, I think I've noticed mostly it always occurs on ESP stuff, where high and low seem to be in reverse. So let's close this workspace. Take this one off. Now we're up to the itsy bitsy. And this is where we migrate from LEDs to Neopixels. And this happens to be, and you can see. So let's open our CircuitPy drive. So this one we'll probably have to correct the path on. So File, Open Workspace. And we'll open this one up. Since we updated to 6, we have to look here. Yeah, this one got updated. But we see the yellow on the code. So VS Code has got an issue. So this one's still 5. So 6. 6. Save it out. Now the red's gone, yellow, the tiddly's gone away. So this one uses a Neopixel. Now I'm just going to choose, I apparently haven't chosen the board correctly in here, so this is ITZY. So we have the itsy bitsy RP2040. I'm just going to save this workspace by closing it for the moment. What we want to check actually on here, this is you should do with CircuitPython controllers a lot. There's that tool, Circup. Whoops, I'm root. I need to be me. CD Control L. Circ up update. If you want to know the commands, that's it. Circup. What I'm after is the update command. So there's an updated bundle. It's updating dunk. Okay. You can also do a freeze command to see what you've installed on here. And in order to get that LED to behave like a Neopixel, not just a one-shot LED, you need this, the Neopixel library. If you install it, it'll put the pixel buff in also. This shows I have at least 2 libraries installed. So let's go open it back up in here. Okay. Now I had 2 codes in here. The reason for that, I was messing around with 2 different versions of the Blink. This is the Neopixel version of the Blink, and this is one LED. When you treat that LED just like a regular one. Okay. Actually, I'm pretty sure, if I remember correctly on this thing, there might actually be 2 LEDs on here. So we can also do that. We'll look at the Neo first and then the other one. So you load the same thing, board time, but this time you also load Neopixel. You find the pixel. This number here is how many Neopixels are in the string. So in theory, this is pixel 1, but if they actually glued on 10 of them onto this board or a matrix, you would have n number of them in here. We can set a brightness. Now, this is 3 colors, so red, green, blue. You set the colors. So if we were to change, this to 128, for example. We will get a different set of colors here. It's kind of hard to tell because it's a pretty tiny Neopixel. But you get the idea. You could, change these two, and you can come up with, RGB color fixes. This is pretty small to look at. You're better off when you're playing with Neopixels to play with slightly bigger pixels, not the one on the controller. They put this in there now because I believe they use the different colors to tell you the state of the microcontroller. So if there's an error in the code, or that this can blink 2 different colors, for example, there's some sort of color code associated. I don't have it handy, but I heard them on one of the Ask an Engineer shows talking about this, that they added this functionality per request from people to actually indicate what the state of the board was in. So now let's go look at the other code, this one here. So what we're going to do is we're going to actually rename this one, and I'll call it 2, and we'll rename number 1 as code. Doink. Control S. Now we are only blinking the other LED. That's right, this one right up here. Now this is the pure standard LED. So not only can I do the Neopixel one, I could come in here and merge the 2 sets of codes together. Like I could go in here and say I need this import right there and put it in here, and then out of here I need this chunk. Sorry, I need this chunk right here. I can come back to here and we can put this like so, and then in here we can go like this, and we can do this like so. There you go. Both of them in action. The reason for this not changing much, the Neo, is because the while loop is not correct for doing this. So it's the while loop is the code is expecting you to cycle through it rapidly, and what we're doing is we're blinking one set of LEDs, then running this in one pass, and then resetting it all again, right? So that's why it's only like blinking blue and green or something like that on this other one. It's just a code issue. It's nothing. It's not that there's anything wrong with it. But you get the idea. That's this guy. Now we get to look at some lot more wordy code. It does effectively the same thing as this Neopixel, but ESP-IDF has its own unique way of doing things. So we'll close this workspace off. And of course, being polite, we'll dismount this correctly, like so. Now we go to this. Now, in this board, we have to make sure we pick the right one of these. So I'm going to use the UART connector at the top. Okay. So let's go open the folder. I might have a workspace for this actually, so let's open a workspace. Open workspace. And we want projects, Blink it, ESP32. Yep, I do have a workspace for it, so we open it. Okay, so this thing is in ESP-IDF mode. You can tell because the bottom of my bar here is super long. All this stuff on this side, just before the house, is all ESP stuff. Then you have this. This is platform I/O, and then all this is related to ESP. Okay. Now this yellow on CMake list, this looks like it's an error, but from what I understand, this gets actually correctly invoked when you actually do the make. And then it's correct. Just to outside of it is incorrect. And the other thing I haven't managed to fix is if we look at here, this is a bit waffly here. Sometimes I'll open this up in this Visual Studio Code's IntelliSense and IntelliCode can't figure the headers out where they are. And other times it can figure where the headers are. So I haven't tackled this problem yet to make it's just cosmetic, more or less. So we'll get there to that. So what we have here is a very big set of code. So we load all this crap in. Okay. Now what you're seeing in here is actually depending on the state that the board is set to. Is it using a GPIO pin or using the RMT system to run its version of a Neopixel? So, and that is all done in a config. So if you have all this set up correctly and you hit this configuration thing and the config editor comes up, give it a moment here. This, if you go into here and you say LED, I'm using the RMT addressable LED at the moment. You can also go into here and say GPIO and example configuration, blink the LED type, and there's a pick list in here. And normally it's mapped to pin 48. In fact, it is written on the board. And it's kind of hard to read it because I have to put my finger over the super bright light. But if you look down here, there's a little writing somewhere on the board that just says, yeah, there it is. RGB at IO 48. That right there. So you can change which one you want. So in our case, and there's lots, believe me, there's lots of frickin' settings in here that you can play with. We're not going to take it out of RMT. So what this is really doing is we figure out what we're defining and what we're using. So in this case, we are using RMT. This config blink RMT, if defined. Right? We're going to use this block. We're not actually using the other block, this one. This is the GPIO one. Sorry, this one is the GPIO one. This one is the RMT one. And this does the pattern of the RMT one. So there you go. See, I don't know where my include file is. Now it finally figures out it can't figure it out. Yeah, right. Okay. Now the other thing too, ESP-IDF tends to write, I would call it fairly strict C code. So you see this uint 8_t. Well, if you remember the old Microsoft book on labeling variables, they had it's called the Hungarian method or something like that. What you're really seeing is unsigned int 8-bit. Now I can't tell you what the T is because I don't remember, but that's the idea behind this. In theory, if I just put int, it should also work. But the int will be determined by at the compile time, but what type of int it is. You can get an 8-bit int, a 16-bit int, a signed int, an unsigned int. You can get a long int. You can get a long int. It goes on. Like, I mean, because of the way the CPUs are these days, if you go back way to like when you compile C programs on a 386, for example, right? And you had, like in the early 90s, when you first had Linux out, for example, right? The ints were the same as the Windows ints. But as soon as POSIX showed up and all that stuff got put into Linux, you started getting problems where you had this piece of C code and you said int in Linux, and Linux gave you a 16-bit int by default, even though you thought you had an 8. And then Windows would say, no, you're an 8-bit int, right? And of course, if you push the number way past the 8-bit, the bittiness, right, Windows would puke, Linux would be still fine, right? So they came out with this idea where we'll just explicitly define what ints are ints, right? Or floats, or whatever it may be, right? So this is where you get this uint8 stuff. In our case, we define the P strip. We got a blink period. You can go on it. Yeah, you can see, for example, this thing is not doing its code inspection properly. We're setting the colors up here. You can see this right there, the 3 colors. Now, we see here, if it was on the GPIO mode, we'd run these functions. Then we come down to here. This is where actually the blink really occurs. Turning the LED on. We run the pattern, blink LED. We run the pattern LED. So what really you're doing is you're blinking it once and then running the pattern. And what I did down here is by default, blink period here was 1000. I took it out and changed the timing on it. So, I mean, if I change that to 500. Now let's see if we can actually compile and push. Now, as I said before in ESP-IDF, when you're flipping around like this in it, your best bet, of course, is to hit the trash can and do a full clean. Okay. Now I'm just going to check to make sure we are on the right port for this. T2I USB 0. Okay. So we are on T2I USB 0. We are doing a 32S3. Now I ran into an issue where it kept wanting to run the OpenCD debugger. That's the thing you put onto here on the debug port, and it's that little thing from STM32 or whatever that you run it through a debugger and program it. If you're getting this effect where it keeps prompting to start the OpenCD and then it can't do it, come in here first, right, and go into your settings for the overall Visual Studio. Go into extensions, go into ESP-IDF, and if you scroll down a little bit, let's see if we can find it. There's that OpenCD crap. Paths. By the way, there's a quirk in the syncing tool here in the corner. If I were you, not open remote, but in here, this, where it says settings sync. I had literally the Windows settings, the paths, show up in the Linux paths, and then blew the ESP out of the water. Up to this point, I would suggest highly that you turn sync off, so that the Visual Studio codes you might have across different platforms aren't sharing their settings. I haven't submitted a bug about this yet, but apparently in this one it's not happening, but it was happening in my virtual machine Visual Studio Code. So we keep going down. There's our flashing baud rate. This is the one we are after, the flash type. In it, UART JTAG. By default, it'll be on JTAG. If you do JTAG, it's expecting a programmer. This is not what we want, because then that just adds a layer of work we have to do. So we make sure it's on UART. If you do run into the issue where the syncer puts the Windows paths into all the Linux areas, just open that settings up and find all the path statements for Linux and just clear them all out. And probably turn sync off, run the setup wizard again to reinstall ESP-IDF and set everything up again, and then you'll be fine again. As I said, this particular Visual Studio Code on this particular Linux box is not exhibiting the issue. I did have it on the VMware one. And that was a couple hours of debugging to find out what the heck actually happened to the settings. So we're going to try building this. And as you see, the problems is all stupid problems. I don't understand why they have come up with this. This path is technically not correct. There's an environment variable in the front here that's supposed to be there. So let us build. We'll hit the build symbol. Doink. Yes, this is a more complicated build just to build a Blink program. As you can see, 1,036 steps to do it. But we have it. Now, you know you're doing the right card, the right port and stuff actually by the steps. If this comes up and says 1014 on this code, right, you're getting the JTAG version. If it comes out like something like 1036, a little bigger, you're getting the UART version. And believe me, you cannot just blindly change the programmer without doing a clean and rebuild, because it stores stuff in the SDK config and stuff like this about how it's going to program the board, what speed, all that usual stuff. And if you don't clean after you change the way you program, it'll just barf big time. So we're going to try to push here, hit the lightning bolt. There we go. No problem. Okay. So changes color, blinks once. There you go. So that's the Blink program on here. Now, let's take out the pattern LED here. So we're just playing with the actual Blink. Okay. Now, since I haven't changed program or anything, I can just hit the lightning bolt again. It'll redo things just enough to put the changes in. See? Well, maybe not. Let's do a full build. Oh, I saw a problem right down there. What's it coming? Void pattern LED. Oh, just define not used function. Whiner. Again, as I said, the C on here is fairly strict. Now you can see all we're doing is blinking. If you're wondering why the color seems to be a little reddy white, it's because I changed the colors of the Blink. It is, after all, effectively a Neopixel. So if you were to scroll back up here, not the pattern one, but the Blink one right here, it's right here. If I was to go 255 0 0, Control S, build it again, and push it again. Now it's red. Because 255 in the first one and 0 0, that's red. No green, no blue. Right? If we want to blind our eyes, we can. So 255, 255, all three colors in here. And I don't think we've actually done the brightness set on here. I can't remember if there's one down here or not. No, there isn't. But I'm pretty sure there's a function in here to control brightness, so we don't blind our eyeballs. So push another one. So once you get into the flow of this, it's fairly quick. It's just the initial first program. There we go. Yeah, even on the camera. Here you go. Blind your eyeballs out. Yeah. There we go. So there's all these different ways of doing blink and what to watch out for. So if you use the GPIO on this S3, effectively what you're doing is just blinking one color. I believe it's always red on here. If you're doing the RMT, here can change the color to whatever you want. This is no different than the Adafruit's Neopixel library in CircuitPython. Now, I saw on Adafruit that Scott has uploaded preliminary, probably betas, for CircuitPython for the S3s. So if you don't want to do ESP-IDF on this thing, you can do CircuitPython now. Now, I haven't seen Arduino method for this yet, although the company talks about this, like the ESPIDF does. They do mention that they're working on it. So given another couple of months, we might actually see all three frameworks in here. So you can do ESP-IDF, Arduino, or CircuitPython. Now, a fully functioning CircuitPython on this board, this makes it one frickin' powerful board. I don't think people realize how much more oomph than any of these other boards this has. I think the only one that might come close to it in oomph is the Pico. But the Pico, of course, lacks Wi-Fi, Bluetooth. This doesn't. This has Wi-Fi, Bluetooth, and there is a model they don't have in stock anymore in Adafruit that actually had 32 meg of storage, and I think it was 4 meg of PS RAM, or 8 meg of PS RAM, something like that. It's a ridiculously large. I mean, think about it. A little microcontroller with 32 meg of space in it. Right? That is a lot. I mean, this is like, I think 2 meg of space for storage things. And I think if you have a Feather, I think this is it. Yeah, Feather RP2040. They actually added in here this right there, a cached storage chip, to give this like 8 meg of storage or something like that. So in essence, this Feather can be a little more powerful than this Pico in what you can do on it, but this Pico has more pins than this guy. So, like so. So, more pins, less storage, more storage, less pins. But this also incorporates a battery on it. And you don't see it, but there's a spot for a JTAG programmer that you can actually stick on there. This one doesn't actually have it. So this is the Feather ESP. That's what it looks like, is that little centerpiece. Here, let me change over to this. There. Oh, and let's unplug that so we don't blind our eyeballs out. And we'll go come in a little closer here. So this guy is super powerful. This guy is probably its next best competitor, but it doesn't have as much storage as these guys do. This guy, RP2040, technically has more parts and stuff than this, but not as much pins as this. This is really good. It has lots of I2C and SPI crap on it, especially if you use the this board with it, which breaks everything out. So I've given this particular Pico Wi-Fi capability by adding this to this board. But you can see all these connectors down the side, all the audio components they put on here. This board also lights up all the ports, so when you have the action, there's all these LEDs in here and stuff like this. Now this is not soldered in here, but this is like this piece here. This is just a protector cap, like so. So this happens to be a I2C port, and this one happens to be a JTAG port because they put the I2C port here. Okay. But I actually have some of these connectors here. I could actually put this on here. It's just a very tricky soldering job to do it. I kind of wish they would just run this off the line and just put the connector on. Although, to date, I've yet to have to actually put a programmer on here. Those ESP32 cams, I've been doing a lot of playing with those, and I'm finding that putting a little programmer on it, instead of using the built-in CH chip and stuff like that, is more reliable to program them. They're finicky to get going. It takes me several times to get it to program, because you're constantly trying to hold the reset key down while it's loading. When I mentioned this on the other ones, these guys here, they don't have this issue as ESP32 cams do. Neither does this one either. Even though it is on here, there's a reset and a boot buttons on here. So, but that is all the blinking you can handle. Well, maybe not. So hopefully this will help when you're debugging something like Blink or something like that, just to get a controller working. You'll know what to look for. As I said, mainly watch out for what they actually call the Blink pin, or whether they not even have Blink in it. As I said, this guy here did not have a Blink LED. In fact, you can see right there, it's missing on the board. It's right, supposed to be there. Right here. And there's a part that goes here too. This is missing from this board. If I knew what it was, I could probably put it back in and we would have blinky lights. So we have a transmit, receive, and a power light basically on this one. Hopefully this will help everyone. And I'll cut this video here. So have a nice morning.